Hello everyone and welcome to this my video on separation of variables, part of the Specialist Maths Units 3 and 4 course here in Australia, but pretty much used throughout the world. So hopefully you're going to find this useful. My name is Darren from Maths Guru. Yes, I say this every single video, but it's my little corner of the interweb where all these videos and downloadable lesson notes are available. What else do I need you to know? Oh, can you subscribe to my YouTube channel? That would be amazing. Why? Well, A, I'm needy, but B, I don't get any feedback. No one really says, dude, this is great. But by clicking that subscribe button and clicking the like button, it really does support what I'm doing. It says, you keep going. You keep talking to yourself in a room on your own. Please keep doing it because, you know, we imagine you're going more and more insane as you're doing it. Right, behind me are my learning objectives. What are we going to do? Know how to use the technique of separation of variables to solve differential equations of the form shown below. I can do that. Now, what we're really saying here is if we can get some sort of function expressed in terms of an x function and a y functions that are multiplied together, then we can integrate it because, let's go back to what we did in the previous video. If I actually reciprocate this and say that dx by dy is 1 on f of x times g of y, well, I can actually move my f of x up here. So I'll get f of x, d of x, is equal to 1 on g of y, d of y. Put some integrals there, and ka-ching, we are back to something pretty funky, right? Differentiate a function with respect to x, differentiate the function or the reciprocal of function with respect to y, and lo and behold, we are good. Right. Now, all of this is about solving differential equations or going back to my original equation or whatever else. It's going to build on those techniques and we want to be able to use it more and more. And there we go. We have the theory that I've just gone through. You'd imagine I would have read these slides before I actually created them. Lol. Right. So let's move on and then have some examples. Yes, goodness, this went on for pages, isn't it? Let's use that theory now. Okay. Now I always start from first principles. I don't like to make a mistake. I always have this idea that someone somewhere is going to trick me. So, here we go. Here's my function of x. Here is my function of y. What can we do now? Well, I'm going to move this down and I'm going to move that up to sort of shortcut the process. So what I'm going to end up there, 1 on 1 plus y squared dy is equal to e to the power of 2x times dx. Put a set of integral signs in front of those and, whoa, make that integral sign actually look like an integral sign, and life is good. Why? Because we can do both of these. We can see here that that is going to be one of my inverse trigonometric functions. How do I know that? Well, A, I've done 1,000 of them, but B, that VCE formula sheet sits with me all the time so that I can just refer to it and go, yeah, not going to be tricked here. So when we do that, when we integrate this, we get tan to the minus 1 of y. All right, now we're going to put plus c1 because when we integrate, we've got some sort of a function. What do we got here? I've got e to the 2x is going to give me a half, e to the 2x plus some sort of function c2. Now again, what I can really do is say, well, if I was to take away c1 from both sides, I can redefine this and say, well, let c be equal to c2 minus c1, and I can just effectively just write 1c on there. Right, what are we going to try and do now? We want to try and get y on its own, so I'm going to get y is equal to the tan of a half e to the 2x, he says, trying to write 2x plus c, close my set of brackets. That's it, really. Half of e to the 2x plus some value of c. Right, find the solution to the differential equation given by that. Now again,